Okay, hi folks. So just now we're going to look at conservation of energy, and we'll start with the learning intentions. So we can see that the first one here, I can state that energy is never created or destroyed, it is only conserved. And I can identify and explain energy conversions and transfers. We should have done that already. We did that on the Monday lesson. Um, Looking at the formulas, which is I can use work done as force times distance, potential energy, mgh, and kinetic energy, half mv squared. We have done that as well. So what we're going to do today, we're going to look at this, apply the principle of conservation of energy to examples where energy is transferred between stores. And I can use work done, potential energy, and kinetic energy to solve problems involving conservation of energy. Okay. So what do we mean by conservation of energy? Well, if energy can't be created or destroyed, it can only be transferred from one thing to another thing. Then if we have, say, a set amount of, well, the classic example, if it's potential energy, then assuming no energy losses, all of that block of energy will be transferred. If it's an object that's falling, for example, all of that energy will be converted into kinetic energy. And if we were looking at something like a pendulum, so here is our pendulum, and we draw it back so it moves up to a new position. The gain in height would correspond to the amount of gain in potential energy. So it would have gained a set amount of potential energy, or potential energy would be EP is equal to mgh. So if we release this pendulum, it's going to accelerate downwards, i.e. the velocity is going to increase. And it'll get to a maximum point here, so the velocity of the pendulum bob is going to be at a maximum point here. And what will have happened is that all of the potential energy here will have converted itself into kinetic energy at the bottom. Now, as it continues swinging, it's going to continue up like this until it will reach a point. Now, if we're assuming no energy losses, what we'll find is that the height that it gets to here will be the same height as you pulled it back in the first place. And so at the point it comes back, it's stationary here, so there's zero EK, it's all EP. As it falls down, the speed increases to this point where it gets back to its original state, and all of the gained potential energy has been converted into kinetic energy. It'll continue on, and as it continues on, it's going to slow down, so the kinetic energy is going to decrease, but the potential energy will increase. And so at this point, it'll be stationary again. It'll be zero EK, and it'll all be EP. And so that's basically what conservation of energy means. If we look at an example, so let's say we're going to get a tall building, and on this building I'm going to climb a ladder. So I start at the bottom of the ladder, and just say, for example, I'm going to carry up a 5 kilogram mass. Now, as I climb up, I'm going to have to use energy. So that would be the work that I'm doing to climb up the ladder. It's hard work. And it'll be even harder because I'm carrying a 5 kilogram mass in a backpack or something like that. So as I climb up, I'm going to use energy. I'm going to use my chemical shreddy energy. So I'm going to be doing work, and in doing so, I'm converting that energy into potential energy. and that potential energy is going to be stored. And so once I get up to the top, and there I go, I have my 5 kilogram mass that I carried up to the top. Now, I climbed up, I got extra potential energy myself. I'm not going to jump off because that would be very bad. But I am going to throw my 5 kilogram mass off. So in me raising this 5 kilogram mass up of a certain height, I've given it potential energy. And let's just say I'm going to go up 100 meters. So tall ladder, 5 kilogram mass that's now 100 meters off of the ground. And if we want to work out what the potential energy gained by this 5 kilogram mass, we'll have EP is equal to mgh, which is going to be 5 times 9.8 times 100 . So we'll have 5 times 9.8 times 100. We're going to have 4,900 joules of energy. So that has gained 4,900 joules of energy by me carrying up the ladder in a backpack. And now, so that's the EP at top. So I'm going to drop it. And this is going to fall 100 meters. And as it falls, it's going to gain speed. It's going to pick up speed, pick up velocity. And so by the time, just in the instant before it hits the ground, it's going to have converted all of that potential energy into kinetic energy. It will be back to its original state where it has zero potential energy. The work that I've done is converted into potential energy. That potential energy at the bottom will now all have converted into kinetic energy. So what I'm going to do, I'm going to make a statement. I'm going to say energy is conserved. And I'm going to say EP at top is equal to EK at bottom. Okay. Then I can say, well, there's 4,900 joules of potential energy, and that 4,900 joules has all now been converted into kinetic energy, and we know kinetic energy is half mv squared. So I can calculate now the velocity that strikes the ground with. I'm going to take my half over to the other side. So we'd have 2 times 4,900 is equal to, now the mass is 5 times v squared, which will give me v squared is equal to 2 times 4,900 all over 5, and finally v is equal to 2 times 4,900 over 5 and the square root of all of that. So we'll have the square root, and again I'll do this all in one, and so I will just type it as I see it. I'll get the square root first, I'll get my fraction, and then 2 times 4,900 divided by 5, and convert that, and I get 44.3 meters per second. So that's conservation of energy. Now, if we look at another example. So, now Now, if you know me, you'll know that I like to cycle. I'm going to go and cycle up a big hill. I'm going to vertically gain an altitude of 300 meters. The hill is 2 kilometers long. Now, so there's me on my bike. Now, if I take my mass and the bike's mass, then we have a combined mass of 80 kilograms. Now, if I just stood there and didn't have brakes on, didn't have anything, if I was just on my bike and I wasn't actually pedaling, then I'd roll back down. Now, I'd roll back down because gravity is going to be pushing me down, although gravity's going to be acting down. That way we're going to get pushed down the slope because of the effects of gravity. So I need to apply a certain force to the pedals just to keep myself stationary, and therefore if I want to travel up at a constant speed, I've got to apply that same force. So Newton's first law, the forces will be balanced if you're traveling at a constant speed. And so if I want to travel up this hill at a constant speed, I have to apply a constant force to overcome the slope of gravity. And the force that I need to apply, the number is a bit funny here, but is 117.6 newtons. So I have to apply a constant force of 117.6 newtons just to travel up this hill at a constant speed. So the amount of energy that it takes me to go from this point to the top of the hill that's 2 kilometers later will have work done is equal to force times distance. And that's going to be 117.6 newtons times 2 kilometers. Now we have to convert this into meters, so 2,000 meters, and that's going to give me a total energy expenditure 117.6 times 2,000, and that will give me 235,200. Now I would normally round this, but I'm just going to leave it as this number for a second, just so that we can see. Now what happens to that energy that I've used? Well, if we're going to ignore the effects of friction, if we're traveling at a relatively slow speed, as if we're cycling up a hill, then the friction won't be that great. There's very minimal friction in the chain of the bike and the wheels of the bike, because I clean it all the time and it's good. So anyway, so all of that energy, I'm going to assume by the time we get to the top, is being converted into another type of energy, and we're going to say it's going to be converted into potential energy. So if we look at what the potential energy at the top of this hill, we've gained a vertical altitude of 300 meters. And so again, 80 kilogram total mass times 9.8 times 300. And if we work this out, then we'll have 80 times 9.8 times 300, and we will have 235,200 joules. Again, I wouldn't leave it as that number, but just to show you that these are both the same numbers. So the work that I've done in pedaling up the slope is going to be all converted into potential energy at the top. So in this case, we can say energy is conserved. And the work done is equal to, I'll say, gain in EP. Okay, so I've given my shreddy energy and it's been converted into potential energy. So what I'm going to do, I'm going to turn my bike around and I'm just going to freewheel down the slope. So here we go. I've got to make sure I do this right. I've done it wrong already. Okay, so I'm going to try and get into a nice tight aero tuck there. I'll be going as fast. So now I'm just freewheeling down the hill. And I want to know how fast I'm going to be going when I get back to the starting point. So I'm going to assume that there's going to be no energy losses. It's a big assumption. And I'm going to assume that there's no friction or anything like that. That would be the accounting for the energy losses, but we'll see what happens. So I have 235,200 joules of gained potential energy when I started. As I started rolling back down the hill, my velocity is increasing. I'm accelerating all the way. And what we're going to do, we're going to say that, again, EP at top is equal to EK at bottom. Now, I do want to, every time you're doing a conservation of energy calculation, you will want to make a statement like this. Either energy is conserved or potential energy at the top is equal to kinetic energy at the bottom. So then we can start using our formula. So we have 235,200 joules, and that's going to equal half mv squared 235,200. Get rid of the half first of all, so we're going to have 2 times that, and then my mass is 80 kilograms, and we'll have v squared there. Finally, I'll have v is equal to 2 times 235,200 over 80, and the square root of that. Again, just do this so that you can put it in your calculator as you would see it in the calculation. So we're going to have 2 times 235,200 over 80, and that's going to give me 77 meters per second. That's pretty good. 77 meters per second works out to is approximately 170 miles an hour. Now, that obviously doesn't happen. I would be breaking land speed records and stuff. So it's not going to happen like that. So what's wrong with the calculation? Well, there's nothing actually wrong with the calculation, but we're just assuming that there is no energy losses, and those energy losses would come from friction. Pretty soon after freewheeling down the hill, somewhere here, as the velocity increases, the friction, the air friction mainly, would increase to a point where I'd reach terminal velocity. And so I would never get to 77 meters per second. For a hill like this, I would probably reach terminal velocity around about 15 meters per second, maybe 20 meters per second. But that would be it. I certainly wouldn't be able to go any faster because of the friction. So the calculation is not wrong as long as we're ignoring real world things. So there we go. One other thing with the, the, the conservation of energy, just to make you aware, and you're not expected to do this uh, at all, but it can be used as a shortcut. If we go back to our original example of dropping an object off of a building, and so I'm going to do this algebraically rather than numerically. So we have a height, i.e. the height that the object has gained, gravitational field strength, which is going to be 9.8, but we'll just leave that as g. We've got a mass of an object, we've got the velocity of the object as it strikes the ground, and so we can look at this, we can say EP at top is equal to EK at bottom. We're going to have mgh, which is the potential energy, so mass times gravitational field strength times the height that is gained, and that is equal to half times m times v squared. Now the object's mass is the object's mass, and that features here and here. So if we multiplied or divided through by mass, both of these would cancel out. And so we'd be left with GH is equal to half V squared. Get rid of the half, multiply through by 2, so you're left with 2GH is equal to V squared. And finally, deal with the square, and so we would have V is equal to the square root of 2GH. Okay. Now you won't find this formula in your formula sheet, but it is a perfectly valid formula to use if you can remember it. If you're going to derive it, you'd be as well just doing the calculation as we've shown you before. But if you do remember it, feel free to use it. I would still make the statement here, because you're going to have to tell examiner, whoever else, that you know that energy is conserved. Okay. Now if we look at the original example that we did, so we had 5 kilogram mass falling 100 meters, and so if we just use this in here, so V is equal to the square root of 2GH, and we're going to have 2 times 9.8 times, it was 100 meters, have the square root of that, we'll have 44.3 meters per second, which is the same here, 44.3, 44.3. So it's essentially the same thing that we've done, just in a lot less steps. You can do it in just a brief formula. Okay, so that's conservation of energy. There's another place where we use it, which you'll come across in space physics when we do that. That's with heat energy, but the principles are exactly the same. Energy is always conserved, and generally will ignore energy losses, just to make things nice and simple for you guys. So wherever you're seeing two different types of energy, you're safe to assume that they're always conserved, and you can equate one to another and solve calculations from there. I'll put a separate post in Classroom to tell you what I want to do now, but essentially there are questions in the course notes. So the course notes do pretty much exactly what I've just done with you today. There's some worked examples in there. And then we have the practice problems. So practice problems starting on page 54, and it goes up to page 57. Here we go, page 57. I want you to do those. However, and I'll detail this on the classroom post, there are certain questions which you will not be able to do. And so I'll go through and I'll find out what you can't do with him. But I will let you know. Okay, right, well, thanks for watching. And any questions, just put a comment with in the classroom post. Okay, all right, thanks then. Bye-bye.